So real quick before we start the talk proper, again, we do host user groups free. We do not charge. It's community thing we do, outreach. And we've got Free Code Camp, .NET User Group, Science Project Society. You see all the list here. We've also got a functional programming group. We've got a bad movie nights. We've got a variety of different groups. So yeah, I host bad movie nights. Feel free to join.
Yeah, that was on my list.
Yeah, it's great. Kai, I can't tell you all. We saw a story of Ricky last time. But so yeah, if there's a user group you're interested in, like we haven't hosted, just let us know. Again, we don't charge. We provide food and drinks, and again, we just kind of tell you about us real quick, share open positions, and then you have at it.
Project Society?
Yeah, it's a Science Project Society, and it's actually meeting tomorrow if you're interested. It's pretty much for anyone who's got any kind of like, maybe side project you're trying to work on or business on the side you're trying to build. And so it's a group where people kind of get together, kind of share ideas, talk to people, maybe talk to people, network. There's even talks about certain things to do to kind of like figure out whether or not you're approaching your side project correctly. It's a pretty cool group if you just go in and just kind of check it out and see if there's anything that interests you. But Side project officially starts at 7. People can get there a little bit earlier, kind of network, but I think officially like the talk starts at 7. There's usually a presentation, and it's a pretty big group. There's like a good 40, 50 people to show. Yeah, they'll like take down the wall and kind of have this entire area in here. And so yeah, if there's anything you're working on that side, you're just kind of interested in like maybe connecting with others and networking, or you can kind of get an idea of what other folks are doing, an interest, come by. And of course, all the Massachusetts Java. We got a functional programming group also, third Wednesday of every month. I'm presenting on the next one, so yeah. Well, I'm doing property-based testing in F#. I'm actually doing property-based testing in F#, and I almost did pick up something at Scala, but that's a whole other thing. Yeah. So a lot of stuff going on. Feel free to ask me if you're not sure about the calendar. I'll figure out a way to keep you informed. We're also hiring, okay, so senior business development manager, account executive, .NET developer, Java developer, DevOps engineers, agile coaches. If you're looking for a job, you know someone who's looking for a job around this area, again, let me know, or reach out to Jesse, and I can get your resume into the right hands and see what happens. Cool. So yeah. And then finally, we do some trainings on like the Scrum certification and so on. So again, if you have any interest, let me know, because we do like Scrum Master training, and we have a variety of other courses. These are just like some of the trainings that we do. That's currently what's current. Cool. Okay, so now we can dive into constraint optimization. For it, sir. Now that I finish my part of the presentation, you can do 100% of the rest of your own, because that's my contribution. Out the door. Out of the door, I'm done. That's just enough math for me. Yeah, should be, once you log in, you should be good. Are you connected?
Yeah. So just what?
Here we go.
Searching for
Searching. It's searching. Okay. And hold on, give it a moment. Give it a moment. Give it a moment. Woo, okay. I just have to kind of shove it in. Okay. Very technical.
Shove it in.
Shove it
Okay. QR code. For that.
Yeah, if you want to scan it, that takes you to a LinkedIn group where we have like links for other meetings and hosts. But again, and this Google Colab notebook also, you all should have access to it. There's a link in the group. It is public, it's available to everybody who wants to mess with it. If you can't get access to it, you need access to it, let me know. I'll find a way to make it happen. But this is open to everybody, so you can fork your own copy, play around with it, experiment with what we did. Our Colab, all of our notebooks are available for everybody in the public for a reason. So
Yeah. Basically a blog.
Yeah. Did you start your recording?
I have not yet. Thanks.
Probably.
Yeah.
Thank you again, Mr. Chu, for videoing us. I appreciate it.
Yes.
Also, yeah,
So we'll have footage from
yeah.
over there and from the screen. We can cut it together, that'd be awesome. All right.
Do it run all. With the star system. Quick run all and then go ahead. So it's on.
Let's do it right all.
Yeah. Run all. Just make sure everything is running. There you go. Okay, and then you start your.
This sheet runs pretty fast.
Yeah.
Okay. So
And yeah, that's supposed to fail.
that's
perfect. Yeah.
That's an expected error.
Yeah. Oh yeah, totally. And then you can clear the outputs. Click on the top, clear outputs.
What?
So go ahead and click run time. And then go to actually go to file. And then clear outputs. You have clear outputs here. Edit. You know what? Don't worry about it.
Edit.
Clear all outputs. There you go. Just so we don't kind of give away. Yeah. There you go. Now we're all prepped and we're not kind of giving away details. Okay, now go for it.
Okay. All right, so just quickly, in case you're new, haven't been to a talk of ours before, this is a user group called Just Enough Math, GEM for short. And what we do is try to talk about math in a software development context. We try to bring, we bring the type of math knowledge to you that will be useful in your software development tasks. All right, so we aim to bring you gems of knowledge from the math world to the software development world. Okay, so that's what we do. My background is in math. Ahmed's background is software development. We've been friends for a long time and talked about a lot of these topics, and found intersections of interest, and so that's why we decided to make this user group in the first place. Right? Get this out of the way. Stick it up there. And so that's what our goal is to bring to you. As Ahmed was saying, all these talks are available as collab notebooks, which, if you're not familiar, it's a new tool provided by Google. It's basically a Jupyter notebook in a highly shareable form. You'd share it just like you would share a Google Doc or a Google Sheet or whatever.
Yeah.
Okay.
And all the examples are in Python.
Right.
And the collab notebooks, you can install other packages, and they manage the environments and sandbox. So it's good to experiment.
Yeah. So all of our code is written in Python. Right? We haven't written anything that's not in Python.
Not for this group.
Yeah. Okay. All right. So last point to mention about the user group is that it's collaborative, meaning participation is encouraged and feedback is highly encouraged. We'd love to hear what you find useful, what we could change, suggestions for future topics, and maybe eventually we'll kind of move to like a more what do you call this format? Where people are just kind of working on projects together.
I was on workshop time before.
A workshop format at some point, something along those lines. We don't present ourselves as experts on these topics. However, we both have strong enough backgrounds to realize when something is useful, and to have tried, and everything we're showing you, we've tried it ourselves, and we see the value in it. Right? So, in particular today, Ahmed will present a case study that is based on a real problem that he worked on in this role.
Yeah, we're actually still using these techniques to solve it, so the actual work.
So today, the topic is optimization, and just to be clear, this is not optimizing your code to run faster or anything like that. So it's not optimization in that sense. This is mathematical optimization. We'll get into what that is in just a sec. So your code, by the way, might incidentally run faster if you use these methods, but that's not the point. Okay. So we're not optimizing code here. What we're doing actually is we're excuse me, trying to build a framework where we recognize when we're looking at a problem, whether or not it can be fit into the framework of mathematical optimization. And in particular today, we're going to be talking about a subset of that, which is called linear programming. Another unfortunate coincidence of terminology. It has nothing to do with programming, but it's called linear programming. It's a subset of optimization. And so that's what we're going to focus on today. All right. So first things first, what is an optimization problem? Just very generally speaking, when you've got a quantity in your life, in your situation, at your job, or whatever that you'd like to optimize, meaning one of two things, you'd like to either make it as large as possible, given your resources at hand, or you'd like to make it as small as possible. Right? So, typical example that you'd be considering would be like, well, I'm trying to make money. I'd like to make as much money as possible. Right? I'd like to maximize my profit. Or if I have some sort of a risk model, perhaps I'd like to minimize the risk, of my investments, or I'd like to minimize my costs that I have to incur to get some job done. Right? So these are situations where you're looking for an optimal value, and in order to achieve that optimal outcome, you have some things that you'll have control over, right? Some things you can control, some things you can't control. The things that you can control that directly feed into the value of that quantity that you want to optimize, we'll call those are the things. Those are the variables that you're going to try to manipulate to achieve that optimal value. All right. So there are a lot of common examples of this. A couple I have bulleted here. Okay, if the store manager can decide on the inventory that's kept on hand, maybe they want to decide that in terms of minimizing the space taken up in a storage room or something like that. Or if you have a very interesting example, maybe you have an investment portfolio, and you have a certain amount of money you want to invest, right, to create the portfolio, rather. So you're thinking of creating the portfolio. You want to invest a certain amount in that portfolio in order to maximize your expected return. So that's another type of optimization problem. And obviously, in both cases, you can imagine what are the variables that you can manipulate. Well, in the investment case, just to take one, you have a list of stocks that, and you make the choice. So I'm going to invest a certain amount of money in this stock, a certain amount in this stock, a certain amount in this stock, and so on, right? And you want to find the right configuration of investments to get your maximal return, right? So we'll talk about that example and that's a little bit of length in just a minute. Okay, so basically you're looking at an optimization problem if your objective is to optimize some value, and again, that means either you want to maximize it or you want to minimize it. And you have known variables that exist that the quantity that you want to optimize depends on and you have control over, right? So the goal then becomes to find the optimal configuration. All right, so here's our basic terminology just to get started. So basically what we're going to do, we're going to run through all the math framework, and then we're going to connect that up to software development. All right. So our mathematical terminology is this. We've got these 5 main terms. A decision variable is what I've touched on is that you've got a variable or a set of variables that you can control, and ultimately, when you come upon a solution to this optimization problem, you'll assign them specific values to give your optimal solution. All right. So those are the decision variables, or those things that you can actually make a decision about, right? Okay, the objective is what I've been referring to as the quantity that you want to optimize, right? So your objective might be profit or cost or risk or the amount of space in the storage room or whatever, okay? So whatever you want to maximize or minimize is called the objective. A slight contrast with that is the term objective function, which simply refers to the function that models the dependence of the objective quantity on the decision variables, right? So it's a mathematical function, right? So like f of x equals blah 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 x squared, square root of x, whatever you can imagine. So so that's a mathematical function that models the dependence. Okay. Feasible domain is so your decision variables may not be able to just be anything. It may not make sense for them to just be any old value in the universe, right? Maybe they're not supposed to be negative values, in which case you would have to state that as part of your problem, right? Maybe, as in the portfolio example, maybe you're limited to a $100,000 investment. So your decision variables in that case are those are the literal amounts of money that you want to invest. So you can't invest more than $100,000 if you don't have more than $100,000 to invest. So all these types of things form what we call constraints on the optimization problem, which we'll get to in a minute. But the collection of configurations of decision variables that make sense for your problem, right, in the given situation that you have that you're looking at, that's what we're going to call your feasible domain, or sometimes we call it your feasible region. Okay. The optimal solution is that configuration of values assigned to decision variables that achieve your optimal value, okay, of your objective. All right. Any questions so far? It's just a set. Right? So here's an example. In the investment portfolio example, all right. Say you've got your team that compiles these figures for you, right? For stock 1 and stock 2, right? Stock 1 has an expected return of 11%. Stock 2 has 5%. We have $100,000 to allocate in an investment, some combination of investment of stock 1 and stock 2, right? So our decision variables, we're going to call them x1 and x2, like this. And these are simply the investment amounts that you choose. Okay? X1 is the amount you invest in stock 1, X2 is the amount you invest in stock 2. So our objective then looks like this. Okay? Our objective is the return, or the expected return. Okay? So you're going to get, your expected return is 11% of the amount that you invest in stock 1, plus 5% of the amount that you invest in stock 2. So that's your return. And that's what you wish to maximize. Now, as we know, stocks are actually random quantities. This doesn't incorporate any of that randomness, right? So this is what we call an expected return, meaning you may get, the real results will tend to be centered around the expected return, but not exactly the return. So we're not going to talk about probabilities or anything like that. It's just a simple linear model to illustrate the principles here, okay? All right. So that's just, this is just to illustrate what I mean when I use all these terminologies, right? These are the decision variables. This is the objective function, right? The objective is the expected return. We haven't really talked about the feasible domain in this example, but we will get to that. Right? So that's just, we're not going to solve that problem. That's just the same. All right. So first we're going to talk about linear inequality constraints. Okay, so we're going to restrict, there are all sorts of constraints in the universe. Today we're just talking about linear inequality constraints. And then one other called integer constraints, we'll get to that. But, so a linear inequality constraint, right, is a constraint on your decision variables, right, of a particular form. Right, where it's expressed mathematically through these symbols, right? The inequality symbols, all right? Either less than or equal to or greater than or equal to, right? And the linear bit means that the variables are related according to these summations, right? So we have these little, let me zoom in a bit. So we have the QIs that represent just scalars, okay? Just scalar constants, right? So just regular old numbers, whereas the xi are the decision variables themselves. B is another scalar, all right? Okay. So linear inequality constraints are of that form. And we'll see examples of this to make it much more concrete in just a minute. First, let me get this out there. Some quantities just don't make sense as negative values, right? Something like in the investment example, it doesn't really make sense to invest negative dollars, right? So in that situation, you formally introduce these so-called non-negativity constraints that look like this. So if you have n variables, this is meant to represent the n inequality constraints. And they come up often enough that they should be mentioned specifically. All right. Now, it's worth noting that if you think about it for a minute, these non-negativity constraints actually fit into this framework here. All right. You basically set n equal to 1, and you'd see that these in fact technically fit as linear inequality constraints. Okay. So which the upshot is that that keeps us within the framework that we want to be in, which is linear programming. Okay. So any questions so far? Let me know if you got anything. Okay. All right. So let's get back to this portfolio problem, so we can actually see, kind of how one of these things would be solved. All right. So we've got our $100,000 to invest. X1 and X2 are as before. The objective is as before, right? We have our non-negativity constraints here because, again, it doesn't make sense to invest negative dollars, right? So we got those constraints going for us. We've got another constraint here, which is that, of course, the sum of our investment must be less or equal to $100,000. So that's natural, right? So once we've got all that, we can incorporate this basic risk model, which the details are not so important, but what this risk model says is that, well, for every dollar that you invest in stock one, you're actually risking $14 or 14 cents, right? And likewise for stock two. So if we decide as a matter of policy that we want to cap our risk at 10%, we end up writing down this inequality, right? And it might be, just commenting to Ahmed earlier, this might be even a better way to think about it, because what it says is 14% of your investment in stock one plus 4% of your investment in stock two is your total risk on your investment. We want to just cap that to be less than 10,000, which is 10% of your 100,000 that you have to invest. All right. So putting all this together, you get a proper optimization problem, right? Stated this way. So this format is the common way that you'll see in literature and stuff like that for your optimization problem. It says maximize your return, your objective, which is the expected return on investment, subject to your constraint of not being able to invest more than $100,000, plus your constraint on risk, right? Plus your non-negativity constraints. You put all that together, and any pair x1, x2 that satisfies all those constraints, we say that's in your feasible region. That's a feasible pair. Okay. Because there are only two feasible, there are only two decision variables here, we can visualize the feasible region. So if I run this little Desmos widget, we can visualize the feasible region. Looks like this. You may have seen problems like this before. This could be taught easily in a business math class or a high school class or something like that. So our feasible region is this nice polygon shape, right? In fact, it's known that the optimal values for it, in such a case, we have a linear constraints like we have here, and your objective function is also linear, like in this case. Then the optimal values will occur on corners. We're not going to use that here, but that's just the fact that just throw out there. So the optimal value for this problem is going to occur somewhere on one of these four corners. All right. So which one it is, you have to actually do some calculations to figure it out. We're not going to go into all that because again, that's what your software packages are going to do, right? But I just want you to help visualize what's going on. So let's see. So, all right, well, I'll just tell you. So the solution is down here. You can zoom in on it. I'll just tell you the answer. So this is the solution that if you put that into a computer, the right algorithm, this is what you would find. You find x1 is 60,000, x2 is 40,000. What does that mean? It means we invest what? We invest 60,000 in the first stock, 40,000 in the second stock. Notice that it was not what might have seemed like the obvious answer, which is, well, I want the highest return, so, stock one is 11%, so just invest $100,000 in stock one. Why is that not the case here? Because of the what? The risk model that got incorporated, right? So, so this is the solution that comes out, and this is the feasible region. And if you take a look at the values on this corner point right here, you see what they are, right? So 60,000 and 40,000 are the coordinates of that corner point, right? So there's another corner point that represents a solution, a candidate solution. It's not the actual optimal solution, but what is this? It's 0 in the riskier stock and 100,000 in the less risky stock, right? Lower return. So that's not the optimal value. Let me. Oh, okay. I said I had to put it in the objective function. But anyway, so trust me, this is the optimal value actually occurs here. So I would like to prove that too, but I don't think I actually put it in the objective function. Okay. Well, you see it. So this is this. I didn't put it in the next one. So this is that. All right. So any questions so far? So far, so good. I really want to know how much profit or how much return I would make at that optimal solution. Maybe I'll just put it in. What was my objective? 0.11. 11. It was 11% for the first stock, right? I'll call that X1. Plus 0. Was it 9%? I thought it was 4. It was 5. 5? Mixing up the risk and the
4 is the risk, 5 is the...
It was 5. Okay. Thank you. So, sliders in. Well, maybe I don't need the sliders. I'll just put in a point. Right, so, okay, yeah, if I move this point over here, stick it right there. So 40,000. There it is. Yeah. And then I would if I look at this view right here, so this is the objective, right? It says I'll make a return of $8,600 on this point. If I allocate my money that way. If you move in, you start to see that it goes down, right? So there's nothing. So here it's about $5,000. It's going to be about $5,000 investing only in the second stock, right? Over here, it's kind of gets to about $8,000, right? It moves in that direction. It's worth noting that, because the risk model was introduced, the sort of naive solution over here of investing all $100,000 in the first stock is not even a feasible point. Right? So, anyhow, so that's just, again, these are just examples to kind of illustrate, the basic concepts. Feasible region, the objective function, decision variables, etc. So the second type of constraint that we're going to consider is integer constraints. Just means that whatever your decision, your decision variables are, they can really only take integer values to have meaning, right? So like say you're allocating staff or something like that, it doesn't make sense to allocate, 2.5 people or something, right, to a task, right? This, certain values are just whole numbers and that's it, right? And this requires special attention and, as Ahmed will show us, a different solver, right? So you have to be careful to choose the integer solver in the package that Ahmed is going to present to make sure that you get the right optimal solution. Otherwise, you can get very bad solutions, or solutions that are not feasible, as we see in this example. So this is an example of what we might generally call a coverage problem, which we will see more about in a minute, but this is a kind of a toy problem about renting buses. So I've got a group of 500 people that need to go somewhere. I've got a bus company that has two types of buses. One is the big bus, has 150-person capacity, rents at $2,000. One is a small bus, 60-person capacity, rents at $1,000. Okay? So how do I minimize the cost, given the constraint that I have to get all 500 people onto a bus? Okay? So we write down the natural constraints. Let me not jump the gun. We define our decision variables to be the number of buses of each type that you rent. We've got our cost function here, which is our objective function, right? And we've got our constraints on the fact that we have to cover 500 people, right? With some combination of buses. We've got our natural non-negativity constraints, but in addition, we have these two constraints that say that whatever values we choose for the integer for the decision variables, they must be integers. Right? So these are integer constraints. All right, so let's just take a look at what the feasible region looks like. Again, I chose these examples because you can visualize the feasible region because there's only two decision variables. As you can imagine, you can have millions of decision variables, right? This is not, this framework is not restricted in any way in terms of the number of decision variables that you can have. How come it's not? All right, so just plotting the linear inequality constraints gives us this pink region here, right? But the dots are, of course, meant to indicate what? The points that have integer coordinates, right? So only the dots are feasible, right? So up here is our objective function. It's the 2,000, times the first variable plus 1,000 times the second variable. I happen to have it set on what I already know is the optimal solution, but I'll prove it to you, right? So just I will indicate to you. But if we look at the value. So this value is the cost of the rentals, right? So right now it's at $9,000. And that's based on what assignment to the decision variables. 3 big buses, 3 little buses. This obviously is not optimal, right? We want to try to do better. So we move kind of down this way. We say, okay, we're going to rent 3 big buses, 2 little buses. That's 8,000. We say, okay, we can keep going this way. We get down to 3 and 1, so 3 big buses and 1 little bus. We're at 7,000, right? Might try moving this way. Well, now we went up to 9,000. Move down here, we're at 8,000. And we go anywhere out here, it's bigger, right? So really, this is the optimal point right there.
What about the one that is close? I think it's opposite the line like the first one, but so the second one?
This one?
Go down, two, one.
Go down.
Go down, down.
That's 8. Yeah. Okay.
6 is all passing.
Yeah. So yeah. It's a good try. So yeah, this one is actually 7. Right. So around here, that's 8. Right. This one's not feasible. It's 7, but it's just outside the feasible region, right? This one. So outside of the feasible region means what? Somebody's not getting on the bus, right?
So could it be correct to say you're trying to get as close to the limit as possible?
The boundary here?
Does that have any kind of meaning or is just like this area?
So it's not the boundary because look, this one is pretty close, right?
Yeah.
So 8,000, is that the one you showed me?
Yeah.
Yeah, so that's 8,000, but it's not optimal. But there is something correct with your intuition because I think really what it is, is there's a slope downward this way, okay? So as you move like from out here down towards the boundary, yeah, generally speaking, the values are getting smaller, okay? Now that slope is determined by these coefficients here. Okay, so it's not a perfectly even slope, right? Because one of those coefficients is double the other, right? So it's going to be it's going to be skewed to one side. So in fact, it's skewed down here. Right? But generally speaking, if you're moving from upper right to lower left, yeah, you're going down. But then there's also a tendency to move down here towards the x-axis. Okay. But it's not the actual optimal solution is not on the x-axis, right? So maybe we're talking about that for just a second. So if I rent 4 big buses, right, at this point, right, what's going on? I've rented 4 big buses, but that's a little bit overkill, actually, right? Like I don't need that. That 4th bus is going to have a lot of empty space, right? And I've noticed that there's a dependence on the pricing scheme here. Right? We'll talk. I'm not going to get into that because that's what I'm just going to talk about. But anyway, so. Another point is that this is, if we look at the value here of 6,000, we see what? That if I take 3 big buses and 0 little buses, I get down to a cost of 6,000, but again, I'm outside the feasible region, which means what? I don't have enough buses, right? And so, it's worth noting, so if you remember the point that I made about this type of problem, where if we don't have integer constraints, the optimal solution will be on a corner. So for this problem, it will be on that corner, okay? Which doesn't make sense for this problem actually because of the integer constraints. But it will be on this corner without the integer constraints. It will be on this corner down here. Okay. Now that corner has these coordinates here, which I've listed here. Okay. X1 is about 3 1/3, while x2 is 0, because it's on the x1 axis, right? So the second variable is just set equal to 0. It might be tempting to do this problem without the integer constraints, and if you pick the wrong solver, that's what's going to happen. If you pick the non-integer solver, that's what's going to happen. It's going to give you 3 1/3 and 0 as your solution. And that's not going to be very useful because if you naively think, oh, I'll just round that, then you end up with 3 big buses and 0 little buses, which is not going to satisfy the coverage. It's not going to give you the coverage you need. Not all 500 people are not going to be getting on a bus, right? So don't make the mistake. This is a pitfall, all right? Don't make the mistake of forgetting the integer constraint when you're using a solver, right? And then just rounding your result because you didn't get integers like you expected, right? You say, well, I need integers, so if you just round the result, you might end up even outside the feasible region. So this last bit I just want to mention is just formally, I've talked about it already, linear programming. This is the linear programming framework. Again, this is what we're talking about today. So you have a linear objective that looks like this and a linear inequality constraints that have this form that we talked about already, right? Okay? Or possibly with a greater than or equal to sign. Okay? So a linear objective means what? Means that it's just coefficients, if you have n variables, you have a and coefficients. The PIs here are the coefficients. Okay, so it's like 5x1 plus 2x2 plus 7x3, that kind of constraint, less than or equal to 100 or something. Okay, or greater than or equal to. So, and if you have integer constraints, we'll call it an integer problem. Without integer constraints, then your decision variables can be fractional or non-integer numbers. We call it a continuous problem. Okay, I think that's all I really need to say. So again, Ahmed is going to talk about how we put all these, this basic framework into practice, introduce an actual solver called OR tools, and to see some results. So, any questions on anything?
So this reminds me a lot of machine learning models where like the queues would be done like your weights.
Yeah, that's so this is what I would call, generally speaking, like a linear combination of, a vector of numbers and really just two vectors of numbers. So one, in this case, is an unspecified variable, but, and yeah, in the machine learning context, often that's just a weighted sum. Yeah. Depending on, this is probably often in this context too, this would be a weighted sum. Maybe, depending on, what the individual, the specific decision variables mean that you're working with. Take that interpretation.
And you can use this to build machine learning models. Machine learning models are actually just built through optimization models.
Yeah.
And that's something we might, maybe we have time, maybe next week, not next week.
Yeah.
Next time, so this is going to be at least a two-parter.
Yeah.
We want to do like gradient descent and non-linear optimization, but like you could build like neural networks and like linear regression and so on, just regression. Because there are actually optimization problems that try to basically minimize the cost function of error. So you actually did it. Yeah, it's pretty sweet.
Yeah.
This builds machine learning models.
Yeah. Not linear programming, probably.
Not linear programming,
but like nonlinear, and that's what we're going to talk.
Yeah.
So today's about linear programming. Next time we're planning to talk about nonlinear. So where you have like a nonlinear objective and possibly nonlinear constraints as well.
Yeah.
So if you have nonlinear constraints, then your feasible region is like some block shape, with curves and stuff, right?
Yeah.
So, and yeah, you might have like a convex, like an objective function that is convex, like a bowl shape or not. Maybe it's also got weird waves in it. So we might talk about that next. And that sort of objective function occurs a lot in machine learning. All right, Ahmed, what do you have to say to us?
Okay. So I'm going to walk you through something I've done with a client also. And this one actually, it's pretty much, again, it's essentially the bus example. If it looks familiar, this is the bus example. You can put the bus numbers in here and it'll solve the bus numbers because the bus example is actually a lot of different problems in real life that hide under different guises, right? But in this case, what we had is, the client had a project-based app that they used online for selling paint. So people would go online, would enter project parameters, namely like the square footage of the area they wanted to paint. And then they would make choices about their paint preferences, like, oh, hey, I've got 1,500 square feet, and I wanna paint it using Sherwin-Williams flat white, right? Okay. And so once they do that, the online store has several different sizes of Sherwin-Williams paints, right? Several different cans that cover different areas. And of course, they didn't want the customers, to go in and pick how many of each quantity they wanted. They wanted the system to decide for them because they wanted a user interface that didn't suck, right? But also because by doing so, they can actually make it to where they can give them a good price, right? So the idea here was like, hey, if we don't want the users to choose the paints, the actual paint quantities, and we want to choose how many of each paint can size we want to give them, how do we make the choice? And so, of course,
To optimize the cost.
Exactly. Well, we want to be competitive, right? So we want to give them the best possible cost so they'll buy from us rather than our competition. So we optimize based on cost. So the whole thing was an optimization problem where the decision variables were the quantities of each size of paint can, and the objective function was cost, and you were trying to minimize on cost. And so in this case, they weren't quite sure, like, at the time they weren't really quite sure what they were going to do with the user interface. I looked and I was like, hey, this is an optimization problem. Let's do this, right? And so here's an example of some actual paint can prices that were pulled from an online store. And this was as of a few months ago. Okay, so and this is kind of interesting because it kind of lets you know where some of the interesting aspects of the problem lie, right? So in this case, I was looking for a particular color and brand of paint, and that site happened to have 3 sizes. Okay, so it had a 1 quart that would cover 100 square feet, right? You cover 100 square feet if you painted with that whole quart, and it costs you $21.98. But then you go to the gallon and get 4 times the coverage, but the price only increased by about a factor of 2, a little more than 2. You can cover 5 times the area from the 1 gallon, and here the price increased by a little less than a factor of 5. And so you see there's this interesting asymmetry in our prices, right? You go, this is the cheapest per unit cost. And yet, when you jump from one to the other, you realize that the gains are dramatically different, right? You're getting major savings here, not so much savings here. And it's this that makes the solutions pretty interesting, right?
Because you're getting like quadruple coverage from here to here versus double price, right?
Exactly.
And then here,
quintuple coverage, and you're almost quintuple price. Not quite. Yeah. And so there's that kind of asymmetry there. And so this is pretty, so it gets pretty interesting. And the thing is, there's a lot of different pricing models, right? I've seen places where the smallest unit was the most expensive, right? And so the price, but generally there's usually this sort of, the more you buy, the cheaper per unit it is, even though your total cost is more. So, and we could probably kind of skim over this one, because I think we're running a little low on time, so we're going to kind of skim over this. I already told you what all this was. Yeah. So one thing about it that's similar to the bus one. So essentially our decision variables are the quantities of how many of each size paint can you want to buy. And just like the bus example, the domain of the decision variables are going to be integers. Because last I heard, nobody lets you buy half a can of paint, right? You got to buy the whole thing in whole units. And of course, you're not going to buy less than 0 cans, right? So here's a question. What do you think the constraints are? We know we want to optimize to minimize the price. We know what our decision variables are and their domain. What's the constraints of this problem? From a customer? Yeah, right. Because the customer enters a project area, so the constraint is we have to at least meet the project area. Just like the bus example, right? You have to let at least as many people on the ride. Because without the constraints, if you didn't have the constraints, it would be very easy to minimize the price. Just say buy nothing, right? Exactly.
yeah.
So the constraints are what really kind of nudge you towards, interesting solutions. Cool. So let's scroll up and I'm not going to worry, since we're not really doing the activity, we're not going to worry too much about it. So before we talk about solving this using a package, I'm just going to show you a sort of naive implementation of how to try to solve the manually. And the idea here is not to say that you should try to do it this way, you shouldn't, but to give you an idea of where some of the nuances of the problems are. There's some tricky edges to this problem. So over here, I've coded up the data, right? We got a price, the list of all the prices, the list of the coverage for each price, right? Coverage corresponding to each price, and then it's turned into tuples right here, okay? So now it's just a list of pairs of price coverage, ordered pairs. Now when we look at this problem, we start to think about it. So think about this problem a little bit. If you were trying to figure out, let's say somebody told you, hey, I've got these paint cans with these prices, and I want to cover 1,200 square feet. How would you go about it to try to figure out what they buy at the cheapest price? Okay, start with the cheapest per unit.
So,
And then you try to, if that's too much, you go right to
so
it. You decrease the amount of the so that you fill in the remaining with the same one. If it still have some left over, then you decrease that one by, by 1 length.
Same as in the more programming, I will basically do something like divide the coverage by the price for each one, then I would sort by the lower to the highest coverage for the price.
Yeah.
And then I would start with the highest, and then I would start dividing and then the remainder, and when the remainder is zero, keep going on to
You're hitting upon the essence of the solution, yeah. So both of you are definitely hitting upon an essence, right? And so yeah, so what we're doing here, right? So like you're saying, so this is the main entry point. Actually, can you go? Yeah. So this is the main entry point to the function, right? So the first thing we're doing is we're sorting all of our paint cans by cheapest unit price first, right? Like you're saying. This way, when we go through the list in order, we start with the cheapest per unit price and work our way down, like you were saying, right? And then, so this basically just does a sorting and calls this main function here. And so here, this one basically gets the current product, right? Keeps track of the remaining products, plug out our pricing coverage. Like you were saying, we figure out how much are we covering, right? Like you're saying, we figure out what the quantity is by integer division, area and coverage. Now if we're not able to cover the whole area, we're basically getting the floor of that number. Then we figure out what the uncovered area remaining is. We're not doing a remainder here just because of the quantity, right? And then we decide whether or not we're done. If we only have one product, basically meaning we only have one product or we're at the end of our list, or there's nothing uncovered, we happen to cover everything, or, this is our recursive case, right? Everything we have uncovered, if we try to optimize at everything remaining on the uncovered area, and it costs more than the price, that's the area where you said determine whether you go right or left, right? This is essentially what you're doing. Do we add that extra item, or do we say, hey, I want to start going with the smaller quantities? Because once you get to that area, maybe it's cheaper to buy extra of that quantity, or maybe not. And this makes that decision, right? So it recursively solves a problem over the remaining products in an uncovered area, and compare and see if this is going to cost more than the price. If any of these are true, we go ahead and return because we're done. We give the current product. And we go ahead and calculate the ceiling of the area by the coverage. That way, if the area is a little bit over the coverage, we add that extra in here. If we haven't covered the whole area, this is equivalent to dividing the area by the coverage. And then, otherwise, we just go ahead and recurse on the remaining products. Right? And we build up, we accumulate what we've calculated so far. Now, this is a very naive implementation. I'm recursing away happily, right? We're probably going to run out of stack space very fast because this is not a functional language. We're not tail recursive, but the structure is obvious. So I went for something that's very obvious structure. In practice, there's a lot more to it. If you want to make this, you'd want to unroll this loop right here. You'd want to figure out a way to have this basically not be a loop. Use heuristics because this is a combinatorial explosion waiting to bite us, right? So when you start trying to make it efficient, it gets to be uglier, right? But this is like a naive, sort of clean, ideal, let's pretend efficiency doesn't matter and we have all the stack space in the world solution. But it tells you the structure of the problem. And it tells you where some of these complexities around that decision point, right? Do I buy extra or not? Do I go right or left? That's what's there. Cool. So does this make sense? Now this is here again just to compare it to what we could do with a package. Also, there's going to be more complexities we're going to throw in here because we're going to start thinking about availability, okay? Which is something that doesn't get handled.
Availability of paint, right? So
Yeah.
maybe we run out of one type of paint, right?
Yeah. We're going to cover that in a moment. So very good. So you're pretty much anticipating the solution, so that's good.
Yeah.
So if you want to scroll down a little bit. Yeah. And go ahead, and you can go ahead and just go ahead and hit it before you play it, even though it's already checked. Okay. And again, here we're just checking to make sure that the solutions are what I know the known minimums are, right? So here I'm like, hey, for 1750 square feet, what do I need? It's like 2,000 gallon of paint, right? That's the cheapest thing. Okay, cool. 2,200, 2,000 gallon of paint. Forget about your 1 gallon, 2 of the 1/4, and so on, right? And you can see, like in this case, for instance, yeah, just go ahead and buy 2. That's going to be a cheaper solution, and so on. And even here, 2205, again, we overbuy here rather than buying 3 of this, we overbuy here because this is the cheaper solution, right? So always making a decision, do I overbuy or not? So far, so good. Any questions? Cool. Okay, so again, that's the manual implementation. Now let's look at it basically by using a constraint optimization package. We know what constraint optimization is. We have the language of constraint optimization. Let's go ahead and pick up a package and look at how to actually do it. So, yeah, so actually, can you scroll up a little bit? Sorry. Yeah, right here, that's cool. Awesome. So, again, this will look pretty familiar, although you slightly, yeah, this is pretty much familiar, right? So basically have a list of variables, P, that's the price of each pink, right? We have a list of those values. And then have the coverage, right? The area each size pink can covers. And of course, decision variables, Q, that's the quantities, right? And essentially the problem is, find the decision variables, Q, such that the weighted sum, or the dot product of Q and P, right, that's basically your total price, is minimized, subject to Q are all non-negative integers, because again, you have to buy whole paint cans and you can't buy negative ones, and you have to meet the project area. Right, multiplying all of Q's by all of the coverages, the dot product, should be greater than or equal to the area. And again, this is the bus example. I can put the bus numbers in here and solve the same thing, because they are the same problem. With constraint optimization, you find that a lot of problems are the same problem, hiding in a different form, which is pretty interesting. Okay, so I'm going to use Google OR tools. Can you pause real quick? Yeah, you need to run it, we're fine here. So I'm going to use Google OR tools to solve it. Now, Google OR tools is a package that does constraint optimization, satisfiability. It has routing problems. People are writing to solve Sudoku puzzles. It's free. It's efficient. Yeah, you can handle thousands of variables. It's pretty industrial strength. It's not the only tool out there. You have others. I believe Python's got one. I forgot what it was called. Size something. It's always been size something. Could be that. So you do have others, right? OR tools is nice in that it's available in a variety of languages too. C#, C++, I believe Java, Python. But it's not the only game in town. If you understand constraint optimization, you'll understand how to solve this in any software. Okay? Okay. And again, like Justin was saying, understand the nature of the problem so you know what solver to choose, right? So this problem right here for paint, it's linear. There are no exponents, there are no discontinuities or anything like that. It's like a weighted sum, linear combination. Our decision variables are all integers, they're all quantities, so we know it's integer. So it's a linear integer problem. And these two are things we need to know what solver means. Linear integer, okay, I know what I need. So here it is in Google OR tools. If you can scroll up. So this is a more generic solution, and it's actually shorter. I just bothered to put comments in here and actually space out lines. So first, we choose our solver. So from OR tools linear solver, remember it's a linear problem, I import the wrapper I want. So I have to know it's a linear problem. And this is where some of the background helps. And then, pretty much what am I doing here? I'm just, keeping track just the length of the list, convenience variable. I instantiate the solver. And in this case, I choose a solver that can handle integers. Now there are a few different solvers that can handle integers in Google OR tools. This is one of them. SAT for satisfiability integer program. There are a few others. But this is one, it works, I think that. And there's on their page, there's a list of the different solvers and what kind of problems they do and even examples. So I just say, hey, give me a solver. Then I say, hey, this is my decision variables. I need n instances of an integer with a lower bound of 0 and no upper bound. Okay? That's my decision variables. Then I say, hey, minimize this, right? That's the sum of the quantity times price. Okay? Then I say, oh, and by the way, I gotta cover the area. So go ahead and add this constraint, right? That's the quantity times coverage. Then I say solve, and that's it.
Do you have non-negativity constraints?
Lower bound is 0.
Okay.
Yeah.
So lower bound is 0, that's your non-negativity constraint,
Yeah.
And then
Upper bound is
this is your coverage constraint, and that's others. And then your integer comes from.
So this is fun. This is fun, and this is weird. You would think that integer comes from int var, right? Int var for integer variable. Fun fact, I've actually gotten floats out of int var when I use a different solver. So technically, int var should, but no, you gotta make sure you use int var and an integer solver. It's kind of weird. It shouldn't be that way. I don't know why. I'm not happy with it, but that's the way it is. So this will give you integer variables if you use an integer solver.
Okay, and you need both of those to get the right.
Yeah.
Okay.
Yeah. And then you just tell it to solve. And then here I'm just checking to see if it even found a solution, right? So basically I'm like, hey, did you not find an optimal solution? Yeah, just choke. At this point, you're like, whatever. Of course, you're going to want to have better error checking, right? Because here you can say, hey, did you give me an optimal solution? Or did you find a feasible solution? Or did you find no solution? And then you can choose to act appropriately. Because it may find that it can't find an optimal. Maybe the problem is too hard, like NP hard, and it can't find an optimal solution, but they can at least tell you some feasible solutions, areas that are in your feasibility region. And for some problems, that's as good as you're going to get, so you take it and run, right?
And you just take that and you say, like, pick the best one and say, well, is that doable for me?
Essentially.
It's in the feasible region, so
So you
presumably it's doable.
You have probably give them two choices.
Yeah, you can get a few
To let
choices.
to let them know that there's no.
Yeah.
To intuitively let them know that there's no optimal solution.
Yeah. Yeah, how you choose to handle it is up to you, but yeah, one way is to like say, hey, I couldn't find an optimal solution. Let's say here's n choices that I was able to pick up. And maybe you could even do some testing on those choices to find which one of them is actually better based on whatever heuristics you're going by. Yeah, absolutely. And that's where it comes in handy to be able to check to see what kind of solution you got, so you can decide how you want to handle it. In my case, I'm just like, yeah, we're just going to die. But in reality, of course, yeah, you'd be a little more robust. And then here, you basically return the value of the decision variable, and I'm going ahead and also return the objective value, which is the total price. Okay? And so an object that are returned here, there's several methods attached to them, and you can get some additional information out. But if you look over here, you basically see this is like what? Essentially, 1, 2, 3, 4. Basically, call it 6 lines of codes. I'm gonna have a little extra check, and I didn't have any other one, extra spacing. So it's very compact, more compact than the last solution. The last solution was very naive too. It would choke if your data got bigger just because of all of the combinatorial explosion. This is more efficient, and most importantly, you can think at a higher level. Because when you look at it, to me at least, it's much more readable. I'm like, yeah, I have my decision variables. I'm minimizing. I know my constraints. Give me my answer. And so it gives you at a high level, it gives you a generic way of solving these at a very high level.
It's readable, especially if you know something about the language of optimization, which is why we covered that at the beginning.
Yes. That makes sense? Any questions? Okay, so can you scroll that a bit? And then here I just basically have it run in some scenarios. So when I hit this, just hit play on the first one.
So here.
No, the note 48.
Oh.
And again, so we get it, we say, hey, it gives me basically a list of the different quantities. No 1 quart, no 1 gallon, 1 5-gallon. Here's my total project price, $200. And again, you can go through and hit each one of these, but you get the idea. Okay, it's returning basically the optimal results that match. Here it's like, yeah, this is what you get, and that's how much it's going to cost you total.
Yeah, this is like more of a mixed result here. You got 2 of the big ones and then 1 of the little ones.
Well, 2 of the 1 course, these are 2 of the 1. These are 2 of the.
Oh.
2 of the, yeah, I actually didn't bother sorting these because I didn't have to worry about it. I let the optimizer deal with it. So 2 of the 1 quarts, none of the 1 gallon, 1 of the 5-gallon. For a price of $243.96.
So 1 big one and then 2 little bitty ones.
Mm-hmm. Exactly. And then and then so on. And yes, you get the idea. And again, it's going to be a lot more efficient, and there's more flexibility. And you'll see where the flexibility comes in handy. Okay, cool. So pause right here. Thank you. Okay, so far so good. Now, where the flexibility comes in handy is when you want to extend your problem. Because right now, I did this, and I'm ignoring the fact that restore might be out of stock, right? Maybe it doesn't have a certain size of paint can, or it only has enough, but not enough to meet your quantities that you want. So now it's like, wait a minute, we have to take into account the fact that there's stock, right? We can't just return a solution if it's more than what we have in stock. How should we address this? Anyone want to guess? Constraints. Exactly.
Add some constraints in there, that's it.
Yeah, add some constraints in there. Yeah. And so the constraint would be, what would the constraint be?
If you have different like cans types, if you only have a specific limit for the big cans, then you say the big can cannot be greater than whatever your availability is.
Did you have one inventory? Okay. So the constraints are going to be basically inventory versus the quantity, right? The cans for the quantity for a particular can, right? Yeah. And this is where it's really, yeah. So in this case, all we have to do to extend this problem is to just modify our constraints. And in fact, in a lot of cases, we can find that we can really modify our solution by modifying our constraints. So if you want to scroll down a little bit. And so in this case, yeah. Now in the manual solution, we have to actually incorporate constraints into that solution, and it's not quite as intuitive as it seems, because it's not just a matter of just slapping a min around the value. You have to actually integrate it a little bit deeply. But in this case, it's super easy. If you want to scroll to the implementation. So here's the new implementation. So here's one. I included a list of stock, right? So this is the stock.
So that's the inventory.
Right, that's the inventory. So I just listed inventory, and here's my change. Are you ready for it? That's it. That's all I have to change.
That's the only code that you changed?
That's the only code that I changed, other than including stock. So, because remember, yeah.
It was ranging from 0. This was the lower bound, right? This was, I asked about non-negativity constraints, right? So that's still there. Then you just added an upper bound.
Right, because yeah, so what happened was, so remember, we can have our constraints by either adding constraints or by constraining our decision variable. Since our quantity can never exceed the amount in stock, instead of saying our upper bound on quantity is infinity, which is no upper bound, I just say, no, it's stock, and I'm done. Otherwise, this is identical, except for, I included the argument for stock. Now, I could have also, if I wanted to, instead of doing it this way, I could have left this originally the way it was, and added my constraints here. I could have said, hey, for every I in n, add that the quantity is less than or equal to stock. So I could have done it this way too. Both would have been fine, but Google does recommend that if it's possible, do it this way because they say it's faster. Okay? And it's only a change in one line. That makes sense?
This is where you generically add constraints, right?
This is where you generically add constraints.
These are specifically like about the ranges, restricting your decision variable to certain ranges.
Exactly. That's the domain of your decision variable. Right. Which again is like you said, is a form of constraints. But yeah. So yeah. And that's it. And we're good to go. We're done. Questions? And again, this is very important to keep in mind is that a lot of times you can figure out, like you can extend your solution and actually have your optimizer do a lot of extra work by just thinking about your constraints, because that's what nudges you in different directions. And so again, we could run some examples like here. Like, yeah, you want to hit, yeah. So here I have like, hey, what if I only have 31 cans of 1 quart, 45 of 1 gallon, and none of the 5 gallon, and I want to cover 2,200 square feet. It's like, okay, well, you need two of the quarts and 5 of the 1 gallons, and this is what's going to cost you. More than if I actually had the 5 gallons in stock, right? Another example here, okay, is what if I only have one of the one quart, right? 45 of the 1 gallon, and only 2 of the 5 gallons, and I need to cover 9,200 square feet. It's like, well, okay, well, you'll need 2, everything we have in stock for this guy. Don't bother with here, and we'll, buy 13 of our 1 gallon. That's going to cost you $97. And then this one, can you hit play on this one? And so this one, I made it a point to give it stock that can't be met. I said, hey, what if I only have 1 of the 1 quart, 1 of the 1 gallon, and 2 of the 5 gallon, and I need to cover 9,200 square feet. Can't be done, right? So I hit play, and of course, it fires the exception because I put the exception, no optimal solution found. Right? And technically speaking, this is probably a no feasible solution, But at least shows also that again, when we can't even solve the problem, we can detect that and we can act on it. Questions?
So this one doesn't find the resolving like 1, 1, 2, like
Right.
the most closest.
Well, it won't because you can't beat the coverage area.
Yeah.
Right? So one of the things about constraints is this, right? Constraints have to be met. So if you can't meet the constraints, then you don't have a solution. If your constraints are not hard constraints, you may want to think about trying to integrate them into like your objective function itself. But if you have a constraint, you're basically telling it, this has to be met. If it can't be met, we're host. That's basically what a constraint is. Because you're basically telling them, hey, the customer wants to cover 9,200 square feet. We can't give what the customer wants. There's no solution. So definitely think about whether your constraints are really that hard. If they're not hard constraints, think about a different way of handling them, maybe through the objective function. Does that make sense? Yeah. So in this case, it wouldn't try to find the closest it can get to this. Because if you think about it, the closest it can get to this is just selling you everything it has in stock, right? Which is a pretty trivial solution.
And from a customer service point of view, if you want to make that recommendation, okay,
Yeah.
try this. Like, but I wanted to cover 9,200 square feet.
Yeah.
Why are you recommending this way? Tell me to go to another store or something.
Yeah.
So,
Well, you cover some of it. Yeah, I'd be kind of pissed if I was a customer and that was the response.
at least get a strong warning.
Yeah.
So anyway, yeah, it returns something, and then you can act on it, right?
Yeah.
However you want to handle that.
So any questions?
This is beautiful. Yeah, very nice.
Oh, thank you.
Thank you very much.
And then if you want to scroll down a little bit, just kind of off. So if you're interested in further info, Google OR Tools has an examples page, right? And again, it's a free package. Anyone can install it, it's free. There's a book called Practical Python AI Project that uses Google OR Tools. It's based on an older version, so it's not the cleanest code, but it is pretty interesting in the way he solves some problems. He even has like a whole logistic regression model that he builds in Google OR Tool as an optimization problem. I don't know if you know about logistic regression. It kind of divides your area, right? Like basically divides your data with a line. And basically he creates the line, and then I think he adds like constraints to like nudge the line and start incorporating data on either side to kind of have a good fit. Yeah, it's pretty interesting what he does with constraints like that. It's kind of fun. Yeah. And then Andrew Ng's machine learning courses, even if you don't do the code, even if you just watch the videos, it's awesome because he does everything through optimization. He sketches out all the machine learning models and optimization. Then when he wants to like make his like expressions more efficient, he's like, oh yeah, let's optimize that. Let's optimize that like the number of expressions to simplify this and make it a tighter model. It's really cool the way he sketches it out. If you just watch it and just see, it's kind of mind-blowing all the things he does with optimization.
Yeah, I can recommend him as a good lecturer.
Yeah.
It's a very friendly, engaging speaker.
Oh yeah, totally.
One of the original machine learning enthusiasts in Silicon Valley.
Yeah, he's good. He's good. And very good theoretical perspective, even if you don't build anything. But yeah. He does use Google OR too. I think he's using Octave. Google Octave.
Yeah,
which,
Octave, which is a MATLAB.
yeah, basically.
So you can use MATLAB or Octave in this course.
You put a kill function and kill the
What you mean, did he or did I?
You.
I didn't. I don't know if Google OR Tools actually has a kill function. I assume it has something built in, but I'm just making an assumption. Because some of the harder problems you can turn on, right? Like I like to say, probably until the day you die, and we'll find a solution for certain types of problems. Although it may probably crash before you die, hopefully. So yeah, you could do something like that, but I think it would actually like give you like a timeout or tell you that, and I'd let you customize it. Again, I'm kind of speculating, but just because I can't imagine them not putting that in. But it might be something I can look into, but I think they've got something like that.
Well, with these linear problems, that's not going to happen.
On your actual project that you.
Oh, yeah. So on my actual project, no, because since since like Justin saying, it was a linear programming problem, and it was actually quite straightforward. The amount of time it would take to solve it was actually nothing. Because yeah, there was nothing really in there that was like non-linear. Even if you had a very large number of variables, you could still crank through without any time. Now, if I was dealing with something that was going to be more like with non-linear or like really weird pricing models, I'd want to at least make sure that I knew what the timeout on the Google OR tools was, or I could customize it and even deal with like non-optimal solutions. Because also, I didn't also account for the possibility that we wouldn't find an optimal solution either, just because it's linear, there is an optimal solution provided you have it in stock. So again, this was a pretty simpler problem where I knew that I wouldn't run into these scenarios.
Yeah.
Well, that's a good
yeah.
question though, Jeff.
And I should retract what I said. Like, with these linear problems, it can happen. You get a massive, because the computational load becomes too massive. But that's if you have some insane number of decision variables, right? So the complexity just increases with the number of decision variables. But I don't know exactly how the integer solver works, but in the continuous problems, it's just matrix operations. So it might be a lot of them, but it's not too complicated. So
Yeah, and I think Google Oracle's pretty much says it's run efficiently with like problems involving like thousands, if not like hundreds of thousands of variables. So for our problem, like involving paint,
yeah,
we weren't even gonna hit 100. So, but yeah, but the argument problems out there where that is definitely a consideration.
yeah.
Other questions? Then yeah, thank you very much.
Yeah, thanks for coming. Have yourself at home.
Yeah, if someone call, hang around, we feel like
Mingle,
shoot the
schmooze,
breeze or whatever, we can congregate out there.
do some math on the whiteboard.
Yeah, you're gonna do some math with him, I'll next door, because I've had just enough math.
It's just enough. Let's go have a beer. There's a beer out there.
It's good.